Okay, hey everyone. My name is Octavia, and I'm a principal security engineer here at Prelude Security. This venue is to host guest speakers on InfoSec topics, and what we do is every week we invite new or seasoned InfoSec professionals, if you will, to come out and talk about some topic. This week we have an intro to Syscalls for Windows malware. We're going to be looking at some different implementations. I'm really excited to have our guest ever since. I've followed their work for quite a while, looking at some of their stuff in NIM and other languages. So this is going to be really, really interesting for all of you today. And with that, I'll hand it over to you, ever since. Thanks for joining us.
Wonderful. Yeah, thank you so much for the introduction, and welcome from my side as well to my intro to syscalls for Windows malware. So this talk is aimed at beginners. We're going to talk about how to use system calls in Windows for writing your own custom malware. I try to keep it as easily digestible as possible, although I know this is hard because there's a lot that we will cover, but I already uploaded the slides and put them in the chat, so if you want to read it again or just take your time and read it at your own pace, you can always do that for sure. So I'm going to start with just telling you a little bit about myself. So most of you probably don't know me, or if you know me by my online handle, which is ever since. My real name is Sven Rath, and I live in Germany. I work as a pen tester at Artec IT Security, which is an IT security company from Germany. And I work in the pen testing team of Fabian Mosch, aka Secure This Shit, who also gave a talk here last month about AV and EDR evasion with a Packer. So yeah, great team. Shout out to my team. Good people that I'm working with, really enjoying it. And I'm doing mostly internal pen tests at my company. So I started off my pen testing career, so to say, doing a web pen test, but soon transitioned into internal pen tests. And yeah, this is also how I get in touch with malware development. But I'm going to come back to that in a second. And in my free time, I like to publish some code under the same username at GitHub. So I'm posting like small open source tools and code snippets, whatever I find interesting at the time. And also I'm occasionally blogging at my blog, which is linked here. So you can check that out if you want to. If you have any questions after this talk that you don't want to ask in the Discord here, feel free to just reach out to me on Twitter, same username handle ever since. I'll be glad to answer your questions, or if you just want to have a chat, I'm always open to having a chat with some of you people. Yeah, awesome that so many people are here. As I said, the topic today is system calls for Windows malware. For the agenda today, I'm going to start with like a short motivational speech, so to say, on why you should even care about malware development, or why you should get into it, why it's interesting, because that might not be obvious to you if you're completely new to this topic or completely new to information security. And afterwards, we're going to talk about what I call basic Windows internals. It's very basic. We're going to look at some assembly code, but don't worry, you don't have to be fluent in assembly or anything to understand what I'm telling there. It's just to get us all on kind of the same technical base that we build upon, and that you need to understand to actually understand the techniques that I'm showcasing here. So we're going to start with talking about privilege separation in Windows, meaning user and kernel mode, or the Windows ring model. Just one slide on that. And afterwards, we're going to talk about antivirus or endpoint detection and response EDR hooks, which is basically a mechanism which is used by antivirus products to kind of check what function calls you are executing. So it's one way that antivirus can detect malicious behavior. And this is what we're trying to bypass when using syscalls. So this is why we're going to talk about antivirus hooks. And finally, we're going to talk about what are syscalls, what do they look like, what constitutes a syscall, and why and how would you want to use them. And then finally, like the main part of the talk is going to be about the different approaches on how to implement syscalls, how to leverage them, to use them in your own malware, and we're going to showcase basically the pros and cons of all these techniques. So we're going to talk about syswhispers, Hell's Gate, Halo's Gate, Recycled Gate, and yeah, some other approaches. So why should you care about malware development? Well, I would say it depends on which side of the security spectrum you're on, so to say. So if you're like me and you come from an offensive side or from the offensive background, meaning you work in pen testing or red teaming, or you aspire to be a pen tester or red teamer, it might already be necessary as part of your day-to-day job, because unless you're doing only web pen tests, where it's probably only needed for some very edge cases, it will be necessary to have some kind of malware development skills if you don't want to rely on like commercial tools. Because in an internal pen test, of course, you want to leverage all these awesome tools that exist, right? For example, Bloodhound or your C2 framework, Meterpreter, Cobalt Strike, BruteRTL, whatever, all these awesome tools that have so much functionality that makes our jobs easier. We want to use them, but if you use them like how they are coming like off the shelf, you're going to get detected pretty quick by antivirus and EDR. So having some malware development skills can actually make you use these tools and smuggle your payloads past antivirus. And if you're working in kind of the red teaming context, of course, being able to write your own malware will be very helpful when trying to stay undetected, because commercial tools can only get you so far. They are super signatured and profiled, but if you write your own custom malware, you will probably be able to stay under the radar much better if you do it well. On the other hand, if you're like on the blue team, on the defensive side, definitely it helps you to understand, if you learn about malware development, it helps you to understand your enemy's tools, right? Know your enemy, basically. So, and this in turn will help you to actually be able to detect them or to write detection rules for them. So that doesn't mean you have to write malware, but it helps to be able to know about these techniques. Also, if you're coming from, for example, malware analysis or reverse engineering, it will definitely help you to recognize these techniques when looking at malware if you know how they work. And yeah, last but not least, I think fun is always a very important part. So it's a very fun way to just learn more about Windows internals and programming in general. Because if you're like me, I come from a Linux background programming-wise. I had no idea about Windows internals when I started this stuff. But you learn very quickly, and yeah, so it's an awesome topic to get into. By the way, I don't know if I mentioned it already, but I have the chat open on my second monitor. So if you guys have any questions that are directly related to the slides, you can just post them, and if I see them, I will answer them directly. But otherwise, we'll also have a Q&A afterwards. So yeah, let's get going with some basic Windows internals. So the first thing I want to talk about is kernel and user mode. So you maybe already seen this diagram on the right, which is the protection ring diagram. And protection rings are basically a privilege separation model that originally comes from CPU architecture, as far as I know. And the idea is basically that you have different rings where applications can operate. And ring 3 would be the least privileged, and ring 0 would be the most privileged. So ring 3 would be where your usual applications are operating, and ring 0 would be where the kernel operates. So ring 3 is called user land in Windows, and ring 0 is basically kernel land or kernel mode. Ring 1 and 2 are actually not used in Windows, so that is not very interesting to us. So as I said, ring 3 is where your usual applications operate. So for example, you're doing your everyday Windows stuff and opening Excel or Firefox or whatever app you use. Even if you started as an administrator, you're still running in ring 3 because you're not like a driver or a kernel application or a kernel mode application. All the normal applications operate in ring 3. So in ring 3 you have some limitations, right? The applications have separate virtual address spaces, you only have a limited instruction set, and you're basically more isolated between each application. And since this is where our usual applications work, this also means that our malware operates in ring 3. Unless you're writing some rootkits or some advanced driver exploitation stuff, your malware is going to operate in this ring. Ring 0, however, is where the kernel operates, and this is basically it's like the Wild West, basically. So all instructions are allowed. We don't have any memory protections. It's like just one giant address space that is shared by all kernel level applications, and you also have full access to the hardware. So, however, you might think now that what happens if my application from ring 3 actually has to access resources from the kernel. So for example, you want to access the hardware to, for example, in the case of Discord, you want to access the webcam, for example. So you will have to have some kind of bridge between ring 3 and ring 0. And this bridge basically is what syscalls are. So syscalls are kind of the interface between user land and kernel land. In the end, syscalls are just specific Windows functions. So they are mostly undocumented, like there's no or not much official documentation on these calls, but they are just some special functions that are in either ntdll.dll or win32udll. So in ntdll, we have the functions prefixed with nt or zw. Those are the syscall functions, and in win32udll, we have those prefixed with ntuser and ntgdi. And the ones in win32u, those are mostly like related to graphical user interface stuff. So those are not really that interesting to us as malware developers. But in ntdll, we have all the stuff that is for accessing memory and memory protections and all the stuff that is more interesting to us. So we're going to focus on the syscalls in ntdll. So yeah, as I said, syscalls are basically the interface between user land and the Windows kernel. So in turn, that means that any Windows API that you're using, even if it's like one of the official documented APIs, if it needs to talk to the kernel, it will end up calling one of the system call functions. I'm going to get back to these questions later on because I think they are not directly related to the slides. So please keep that in mind for the QA later on. But so back to syscalls. Syscalls are basically closest to the kernel that we can get, and this is why we want to use them as malware developers. So let's do a short excursus to EDR hooks. Like I already said, EDR hooks are what we're trying to bypass when using syscalls, and this will make sense in a minute. So the way that EDR hooks are working is that whenever a process in Windows is created, it starts by loading ntdll, which is kind of the bootstrapping DLL, so to say, and then loading all the other modules into memory or into the process memory. And the other modules are referring to other DLLs that are loaded by a process. And then the EDR is also loading its DLL into your process and is injecting small snippets of codes into some of functions of these loaded modules. So for some functions in ntdll, for example, if the EDR wants to hook this function, it will inject a small snippet of code. And this small snippet of code is basically the hook. And what it's doing is it's redirecting the control flow from the function in, for example, ntdll to code from the EDR. And I will show you this in an illustration on the next slide, so it will make more sense if you don't get it like this. But the point is that then basically in this hook, function arguments are analyzed for malicious behavior. So for example, if you're allocating memory, the memory that you're allocating will be analyzed. And then if the EDR detects something malicious, it will, for example, abort the execution, flag your payload, raise an alert, whatever it wants. So if we look at this in this illustration here, it can be seen that on the left we have our malware, in this case app.exe, which calls some function, in this case virtual alloc. And this function is defined in kernel-based DLL. Now, if this function in kernel-based DLL is hooked, it will basically redirect the control flow to the EDR, like the box on the bottom, where it will check the arguments and then either return to actually execute the function or abort it. And then this is forwarded to the actual syscall, in this case ntallocate virtual memory in ntdll. Once again, if this is hooked, it will return the control flow to the EDR, it will check the arguments, and then either return or abort. And then finally, it will initiate a transition into kernel mode, where the actual syscall will be executed. So if we look at this in an assembly level, if you're more like the person that likes to look at code, this is what a hook would look like. So we have a function here. On the right, you can see the function name, ZWMap view of section, and it starts with a jump to an address which is not in, which is in the foreign module. And this is a jump to an address of EDR code. So this is what a hook would look like. Now, if we get back to what I said earlier, that every Windows API call ends up calling some syscall. Let's do that with another example, in this case, open process. On the left, we can see on the top left green box, we can see open process is a function in kernel 32 DLL, which when called will actually forward to kernel-based DLL, which will then forward to NT-open process in NTDLL, which is the syscall function. And this function will then execute the actual syscall. And now all these green boxes are basically points where an antivirus or EDR could hook a function and analyze what your malware is doing. So now if we can bypass all these green boxes and just execute the syscall, which is like the actual syscall instruction, which is this purple box here, this means we basically bypassed all the hooking of the EDR. And this is why we want to use syscalls and what they are for in malware development. So once again, looking at this in like a code form, you can see open process in kernel-based DL on the top, which ends up calling, like on the last line, NT-open process, which looks like shown in the box below. This is the whole syscall. And now this snippet on the bottom is what we call the syscall stub. And this is crucial to understand for all the techniques that I'm showing in a second. So the syscall stub looks exactly the same for every syscall. There's only like one thing that differs. So the only thing that's important here, you don't have to understand all the assembly code, but these two elements are the most important ones. So on the top, we have a system call number, also known as system service number or SSN, which is basically just a unique ID, like you can think of it as an ID that is mapped to some syscall. Like on the right, you can see this syscall is NT-open process, and this is mapped to the number 26 in this case. Yes, I can definitely discuss that later. Yeah, so exactly, this syscall number is mapped to the actual syscall. And then we have the syscall instruction on the bottom. And if this syscall instruction is executed, it basically just tells the kernel, execute whatever syscall is mapped to the number that was stored in the EAX register. So it's not, the syscall instruction is not the actual syscall, but it's rather just telling the kernel, execute the syscall that belongs to the ID that is moved into the EAX register earlier. So this is important to understand. And as you can see, all the syscalls look exactly the same. Like if we have nt-set information file on the bottom, it's exactly the same. The only thing that's different is the syscall number. And also all the syscall instructions are the same. Like this is a common misconception that the syscall is what actually defines which syscall is executed. But if you look at the bytes on the left, it's 0f05. So it's basically the same instruction. The only thing that matters is which number was pushed into the EAX register earlier. So yeah, this is the syscall stub, very important to understand. If we look at SSNs, or the syscall numbers, as I like to call them, there is one big problem with them, because you might think, okay, if we know the numbers, we can execute syscalls, easy peasy. But it is not like that, because these numbers change over the different Windows versions. So this is a table that is from the GitHub repository on the bottom. It's a guy who basically keeps track of all the system call numbers, and depending on the Windows versions. And if you look at, for example, the third one from the bottom, nt add driver entry, you see that it used to be like syscall number 67 in hex, up until on the top, on the rightmost column in Windows Vista, where it then turned into number 68. So that's a portability problem, basically. Like we cannot hard code these values because they might change depending on the OS version, and we don't know what version our victim is running. So to give a brief recap on that, we want to execute code in a way to bypass EDR hooks, right? This is our goal. However, we have some challenges here. We can't use the high-level Windows API because those calls might already be hooked, and this way the EDR would see what we do. So we need to find a way to execute syscalls independently of NTDLL, because if we use the syscalls in NTDLL, those might be hooked as well. So just using syscalls is not enough to bypass hooks. We can hardcode the numbers because, as I showed one slide before, they change depending on the OS version, and we don't know the OS version yet. So, and in addition, we want to do this without alerting the EDR. So the process of doing this has to be as stealthy as possible as well. So these are kind of the challenges that we're facing here. And before I get into the meat of this talk, which is the Syscall implementations themselves, I'm going to have one excursion because I know this question will otherwise probably come up. At least it came up in all the previous talks. So I want to give my 2 cents on the language debate, so to say. So which language would be the best for malware development? In my opinion, it does not really matter that much. You can basically write malware in almost any language that has access to some kind of low-level programming or to the Windows API. So you can use C or NIM or Rust or VBA, C#, Go. You can use obscure languages like V, for example. As long as you can build Windows applications with them, and ideally, as long as they're compiled, you will be fine. Each language has kind of its pros and cons, in my opinion. If you plan on writing like stage zero malware, meaning, for example, shellcode injectors or stuff to get your C2 beacons past antivirus, I would say go as low level as feasible for you. That doesn't mean you have to write everything in assembly, of course, but using something like C or a language that transpiles to C or C++ would be a good fit. Because if you use something like C#, which is based on a VM, you kind of run into problems because you don't know if the .NET runtime is supported on your target or whatever. So I would say go as low level as possible for you. I myself mostly use C++ and NIM, as I already said before this talk. However, that also means I'm going to miss a lot of awesome tools that exist. For example, I'm not a C# guy, but I know deinvoke is some crazy tooling. So yeah, I'm not going to mention that. Also, there's great tooling for Rust and so on, but not my language, so I don't have the expertise to speak on that. But I also linked some interesting projects in one of the last slides. So yeah, definitely check those out as well. So yeah, so much about the technical foundation kind of that you need for understanding these syscall implementations. I now want to go into some approaches on how you would leverage syscalls in your malware. So the first approach I'm going to talk about is what I call the naive approach, so to say, which is using getProcAddress. So if you are somewhat familiar with Windows programming, you probably know getProcAddress. It's basically a function, a Windows API function that gets, who would have thought, the address of a procedure or the address of a function from a module in memory. So what you could do to get a syscall, and this works perfectly fine to execute syscalls, is what's happening in the third block of code here. So what you can do is get a handle to the NTDLL module that is loaded in your process, and you can then use getProcAddress to get the address of a syscall and use that address to call the syscall. So in this case, we're trying to resolve NT query system information. However, there are obviously, because this would be too good to be true if this was the perfect approach, there are some drawbacks to this, and of course they are related to hooking, right? So the problem is, what if these functions are hooked? If you remember earlier, hooking basically means your function arguments will get analyzed by the EDR or antivirus before the function gets executed. And now if the EDR has hooked these functions, they will see that you're trying to get a handle to NTDLL and that you're trying to get the proc address of a syscall. And this is super suspicious behavior, because if you're a normal application, you would just use the abstract Windows API, right? The documented Windows API. The only reason to use the syscalls directly is to do some weird stuff, basically. So you're kind of being suspicious when doing this. And another problem is, of course, since we are just getting a handle to the module of NTDLL, which is already mapped to our process memory, if this DLL is hooked by the antivirus, we are getting syscalls, but we might get a hooked syscall from this module. So as you see, this is really not the ideal approach, although it might be the most might be making the most sense if you think of it at first. So in order to fix this, what you can do is something that is called unhooking. So you can unhook NTDLL, basically remove hooks from NTDLL. And this is an awesome concept, which is pretty simple but pretty genius too. The idea is basically that you're reading a fresh unhooked copy of a DLL that you want to unhook off the disk. Because if you remember how hooks work, it's basically your program is mapping a DLL into memory, and then the hook will be injected into the code. But the hook will only be injected into the copy of the DLL that is mapped into your process memory. Of course, the EDR will not tamper with the actual file on the disk, because it would be ridiculous if your antivirus would change like Windows system files, like arbitrarily injecting code into them. So what you can do is you can, yes, that would get detected by the AV, and I'm going to show why exactly in a second. So the idea here is that you read NTDLL off the disk to have like the function code which is clean from hooks, and then you're going to copy the text segment, which is basically just the code of the DLL, and overwrite the copy of NTDLL which is in memory. So the idea then is that you have code like on the left in your memory map module, so the hooked version of a call, and then you're getting the unhooked version from disk and overwriting it. So basically you would end up with an unhooked version of whatever function you are unhooking, or whatever DLL you are unhooking. But yes, that would definitely get detected by AV, or it would at least raise your score and make you very suspicious. And this is again related to hooking, of course, because what if these functions are hooked, right? We're reading NTLL from disk, which is super suspicious. We're mapping it into memory, although we already have an NTDLL in memory. And then finally, we're changing the memory access of our loaded NTDLL to write access. So again, this is super suspicious and will probably get you flagged. But I think it's still important to know about this concept, because you can also do unhooking with some more sophisticated techniques, and it will probably get you very far. So, but as we saw, this is not really the approach to do when we try to get clean unhooked syscalls. And this is why most of the, or almost all of the modern, more sophisticated syscall techniques are based on SSN resolving. So SSN, if you remember, system service numbers, I call them syscall numbers. They are basically the thing that we want, right? Because if you remember the syscall stub, really all that we need to know is the syscall number in order to create our own syscalls, because we already know what the assembly looks like. The only thing that's different is the syscall number that we are inserting in this assembly stub. So we don't even actually need to touch NTDLL if we know the syscall number. So here's the stub once again, and you see both of the syscalls and the open process and the set information file. And the only thing that's different is basically the 26 or 27, the syscall number. So all that we need to know is this number basically. And then what we can do is we can create our own assembly stubs using, for example, inline assembly, like here, and just insert that number into that assembly stub, because the rest of the syscall always looks the same. And then we have a clean syscall that we know is not hooked because we literally wrote the assembly ourselves. So we can be sure that there's no hook inside. And yeah, so this is the approach that would be in my opinion, the best or the kind of state of the art to go. And there's, again, different flavors or variants of this approach. And the first thing I want to talk about is a pretty old approach, which is implemented in a tool called SysWhispers. So I'm going to talk about SysWhispers 1 here. I know there's SysWhispers 2 and 3, which greatly improved upon SysWhispers, but I think the idea of SysWhispers is just interesting. So I'm going to talk about the original version. So it was created by Jackson T, who's a very good researcher, and I highly recommend you to follow him. It was a tool released in 2019, so already been quite some time ago. And the idea here is that since we already know all the system call numbers, like if you remember from the table on the right here that I showed you earlier, we already know all the system call numbers for the different operating system versions. So if we just find out the operating system version at runtime, we can just use this table to look up the correct system call number, insert it into our assembly stubs, and then we have clean unhooked syscalls that we can execute and basically blind the antivirus or EDR. So this is the idea of SysWhispers. So the way this tool works is that it's a Python script. You invoke it like seen on the top left. You run the Python script. You tell it which system calls you want to use, like in this case, NT-protect virtual memory and NT-write virtual memory. And then it will generate two different files for you. One is a header file, which contains the function definitions. And the other file is an assembly file, which contains the actual syscall stubs for all the different versions of Windows that exist. And it also contains some code which enumerates the Windows version and then chooses the right system stubs for you. Syscall stubs, sorry. So this means all you have to do is include this header file, include the assembly into your binary, or into your program, and then just compile it and use syscalls as every other function. So this is an awesome idea. It works really well. It has some drawbacks, but we come to that in a second. However, there's one part of SysWhispers which is also pretty interesting in my opinion and very important for malware development in general, because SysWhispers doesn't use Windows API calls to find the OS version. So what you could do is use an API like RTL get version, for example, to get the version of the Windows operating system you're running on. But in SysWhispers, the OS version is resolved using a structure called the process environment block, or the PEB. And this PEB is something that you will see in a lot of tools because it's a super useful structure. And the PEB is basically just a data structure which gets created with the start of each Windows process. So once a process gets created, the kernel creates this PEB object. And it's basically just one big object that contains a lot of helpful information about the environment of the process, hence the name process environment block. And as you can see on the right, those are just some fields of the PEB. It also contains the OS major version, the OS minor version, and the OS build number. So we can query this PEB and read these different fields from the offsets on the left, and this way get the Windows version without having to call an API like RTL get version. The way you read the PEB is super easy too, because the PEB address is simply stored in a specific register. So if you're running on a 32-bit system, it's running on the FS register. If you're on a 64-bit system, it's in the GS register. So you can create the PEB without using Windows APIs by simply reading the value from the register, like on the right, using either read FSD word or read GS Q word. So, and then, then you can, from this PEB, you can read the Windows version. And then SysWhispers will choose the right system call stubs for you. However, there are some drawbacks, which is why Sys 2 and 3 exist, but I will get to that in a second, because basically the same drawbacks also apply to the next technique that I'm gonna show you, which is my favorite technique, Hell's Gate. So Hell's Gate is a technique which was used by malware authors for quite some time before this paper was published, but it was basically popularized or given its name, I guess, by Amonsec and Smelly from VX Underground when they released this research paper in 2020. You can find it at the GitHub repo that is linked here. And matter of fact, it's actually very similar to the very first approach that I've shown. Like if you remember the naive approach where you just use get proc address, like first get a handle to ntdll and then get proc address to get the function. Hell's Gate is pretty similar. We're just implementing these functions ourselves without using any Windows APIs. So the idea between Hell's Gate, once again, also involves the PEB, like the same data structure that I was just talking about when talking about sys whispers. And the first step would be to kind of walk the PEB, like walk the fields of the PEB to find the base address of ntdll. So if you go through the different fields of the PEB, at one point you will get to the base address of ntdll. I'm going to show you this in a second. And this is basically a version of get module handle, like you're getting the address of a module without actually having to call this API, so you don't have any problem with hooks. And then the second step is to get ntdll from memory and look at the export address table. So the export address table is basically just a table that lists all the functions of a DLL and their addresses. And then we're reading this table to get the address of our function that we're looking for. And basically this is just our own implementation of get proc address, right? So it's very similar to the first approach that I've shown you, just that we're implementing it ourselves. And then finally, once we got the address of a syscall, we can just read out the syscall number because we know what the stub looks like and we know at which offset the system call number is. So we can just read it from the stub and insert it into our own assembly stubs and then call them. So this is the basic idea. I would say let's go through this step by step because this was probably a lot to digest. So again, the first step would be to walk the process environment block. And as I said, it contains a lot of helpful information, and it also contains information about the loaded modules. So what this looks like is, can be seen here on the right. This is from a great blog post by Alice Climont-Pommeret, which I can really recommend you to read because it explains all these techniques too. Yeah, exactly, John Doe, that's correct. And I'm going to come to that in a second as well. He said if Hell's Gate is, if the ntdll function is hooked, we would be getting the hooked values, and that is exactly correct. But there is an iteration of Hell's Gate that also fixes this problem. But yeah, let's go back to walking the PEB for a second. If we look at this diagram on the right, let's just skip the top left. The thread environment block is not that interesting to us. On the top right, you can see the process environment block and its fields. And there you can see there's this one field called LDR. And if we look at this structure, we can see there's a list entry called in-memory order module list. And this is basically just a linked list, which we can access, that contains all the modules in the order that they were loaded in the process. So the first module will usually be your program, like the actual exe itself, the PE image. And the second entry will usually at least be ntdll. And now by accessing the second entry, we can access this structure on the top, on the bottom right, which contains the DLL base address. So by just walking the PEB fields one after the other, we can get the address of ntdll. So once we have that address, we can just look at ntdll in memory, which again contains a header which contains all this information that you can see on the right. And one part of it is in the optional header, the PE file optional header. We have the export table. And this export table, as I said, is basically just a list of all the exported functions. And if we now go through this table, we can just get the function we're looking for and then read the syscall number from it. So what this would look like in code is like this. If you look at the for loop on the bottom, you basically just go through the functions in the export address table one by one, comparing the name to the one that you're looking for. In this case, NT query information process. And if it matches, you found the address of your function. So this is basically our implementation of getProc address. One thing though, Hellscape actually uses a hash here. It uses API hashing because it didn't want to include like the clear text of the syscall that we're looking for, because again, that is another indicator. But yeah, that just as a side note. And yeah, then when we found the address of our syscall, all we have to do is read the syscall number, which is like what, the 5th byte or something. Read the syscall number from this offset and then insert it into an assembly stub like on the right. And now we have, in theory, clean syscalls. However, as already pointed out in the chat, there's one big problem with this, which is that if one of these syscalls is hooked, the offset would be different, right? Then the syscall number would not be at the 5th byte, because then we would have like a jump instruction in front of it, and suddenly all the offsets are jumbled and we won't get the right system call number anymore. And this is why Halosgate exists. And Halosgate is based on a quite simple observation actually, which is that if you look on the right here, you can see 3 different syscalls, and the second syscall is hooked. So the first syscall is set information file with the number 27. The second syscall is hooked, so we would fail when we just read the byte at the 5th offset. And the third call is NT access check and audit, which is number 29. And now, if you're paying sharp attention, you will see that first one was 27, the second one we don't know, and the third one was 29. So this kind of gives away that these are like just basic increments if you look at them sorted by the address. So if the top one is 27 and the bottom one is 29, the one in the middle must be 28, right? And this is exactly what Halosgate is leveraging. So if it detects that a syscall is hooked, it just looks at the neighbors. And if the one on top is not hooked, it just increments the system call number by 1 to actually get the right system call number. So this is only partially true though, because this was kind of silently patched by Windows. Some syscalls are not numbered in sequence anymore, so this also has some drawbacks. But yeah, this is a simple iteration on Hellsgate which solved this problem of hooked syscalls. Again, this is published by Sector 7, which also have some great malware development courses, by the way. So you can check them out. I saw people in the chat already talking about these courses. They are very good if you want to get into this stuff. And yeah, they also explain this in a bit more depth. But what both these approaches, or all the approaches I've shown so far, have in common, SysWhispers, Hellsgate, and Halosgate, is one problem. And this problem is a suspicious artifact that is basically left over in our binaries if we use these techniques. Which is that if you're doing static analysis and you're, in this case, I'm just disassembling a binary that uses syswhispers, and then you look for a syscall instruction, you will see that there's actual syscall instructions baked into the binary. And of course they are, because we are, if you remember, we are using these assembly stubs, right? Where we basically hard-coded the syscall instruction. And as such, this instruction will be left over in our binary as well. And this is super suspicious, right? Because why would any legit application have syscall assembly instructions inside of it? Like usually syscalls come from NTDLL or Win32UDLL, but they should in theory never occur in a legit binary. And I suspect that this is why, or this is one major factor why you will be flagged if you're using one of these techniques. And also, if somebody would look at like the behavior of your malware and check where the system calls are occurring from, it will see that system calls are occurring from malware.exe or whatever you named your payload. But in theory, again, they should occur from ntdll, so that's also super suspicious. But fortunately, we can fix that as well with a technique, which is the last technique I'm going to talk about in this section. And this technique is called trampoline jumping. So this is a very fun concept. Again, it's quite simple, but it's quite genius as well. Because what happens is we're trying to avoid direct syscalls, right? So what we will do with trampolines is we're just kind of borrowing a syscall instruction from another module. So instead of like calling the syscall, the actual syscall assembly instruction directly in our stubs, we're just gonna jump to the address of a syscall instruction in another module, for example, in ntdll. So we're just gonna do an assembly jump into ntdll, which will then execute the syscall instruction for us. Like a ROP, exactly. It's the same, basically the same theory or same concept as a ROP. So we jump to a syscall instruction, it executes the syscall, it returns, we're back in our code. And this technique is used in RecycledGate, which is an iteration of Hellsgate. It's used in Freshicalls. It's used in my variant of Hellsgate, which I call BouncyGate, but it's basically just RecycledGate. I just didn't know that it existed. And in many more projects. And it solves this problem that we had earlier. We don't have any syscall instructions left, because all we do now is jumping into ntdll. And the other benefit of this is that our syscalls seem to be a lot more legit because they are originating from ntdll and not from our module. So in code, again, like I said, this is super simple. We already have the address of our syscall from whatever technique we used earlier. And now all that we have to do is look for the bytes 0f and 05, because this is what this is the binary representation of the syscall instruction, as you can see on the right. So we just go byte by byte until we find this instruction, and then we have the address of a syscall instruction. And now all that we have to do is basically adjust our assembly stubs that we were using from what is shown on the left, where we have the actual syscall instruction, to what is shown on the right. So we're just replacing the syscall with a jump to a syscall instruction in another module. And that's all that you need to change in Hellsgate or whatever to make it a lot more legit. And yeah, those are trampoline jumps. So very important technique in my opinion, and very, very fun too. And if we now do the same disassembly and grep for syscall, you will see there's no syscall instructions left. All that is left now is a jump instruction to some foreign module. And if you want to revisit this, I wrote a blog post about this exact technique, so you can check that out on the bottom if you want to read it in more detail. But yeah, this is basically what solves this problem of all the techniques I showed you earlier. And yeah, with that, I guess that's a lot to digest already, so I'm going to conclude the section of Syscall implementation techniques now. Also, we're right on time, I think. And I'm going to finish it up or wrap it up with some takeaways. Why did Taylor's gate use the before and after instruction to find the SSN and not just walk the stub until detecting the move EAX SSN instruction bytes? Is a question in the chat. That's a good question, actually. I was thinking the same. And I think the reason is that if you look at the disassembly on the right, that the EDR is also obfuscating that. Let me check if that is true. But yeah, exactly, that's what's happening. There is no move EAX whatever number anymore because it's doing some kind of obfuscation, right? As you can see, it's doing some addition or whatever. So yeah, this is why I mean, this depends on the EDR, I guess, on the way that they inject the hooks um, into the DLL, but in this case it wouldn't work. Could you tell a bit about the Windows silent patch for Halosgate? Yes, I can, although I'm not super deep into it. I just read about this when researching, so I can see if I can find the blog post and put it here after this talk. Basically, what they did is they adjusted just some syscalls to be not in sequence anymore. So that's basically all that I know about it. I think it was introduced in Windows 11 or something, but unfortunately I cannot give you much more detail because that's all I know about that. Another question, apparently Halosgate raises some questions. What if every syscall is hooked? Almost in the numeric order of syscalls. If every syscall is hooked, I think this is Tartarus gate. I don't know which gate exactly, but if every syscall is hooked, what you could do is just, and this is called syscall sorting, which is another technique that I didn't touch upon. But what you could do is you can go to the upmost syscall and assume it has number 1, and then just increment one by one. So you could basically get the order of syscalls, like the order of the syscalls in sequence, and then start from 1 and just increment. And this is what syswhispers 3, for example, also does, or I think FreshyCalls also does it. It's called syscall sorting. So yeah, that would be an approach that should, in theory, even work if every syscall is hooked. So yeah, as I was on the takeaways already, I'm just going to finish it up and then we can have some more Q&A if there's more questions. Yeah, so my takeaways, just to wrap this up, would be syscall implementations are like no black magic. Like I always had this before I got into malware development, I was reading these blogs and really not understanding anything, and I was thinking like, oh, these guys are crazy code wizards that are doing some black magic there to blind EDR. But as you saw, like the actual code is not that complicated, and even many of the techniques are just iterations upon older techniques, right? Like Hellsgate, and then there's Halosgate, and then somebody improved that by just changing a little bit and turn it to recycled gate, and so on. So what I wish for you to take away kind of is that don't be scared, just maybe choose a technique that you like or an existing approach, and then just see if you can improve something or change something, kind of make it your own, get creative, have some fun, and you will get some, yeah, I would say good results, I guess, if you just change some of these techniques and make them your own. Although we've been talking about syscalls a lot, they are just one part of malware development. So if you want to write malware that is as undetectable as possible, so to say, you should also take care of a lot of other stuff. Secure the Shit has a good talk on this. Given on Prelude, it's on the YouTube as well. He gives a good overview on all the other aspects that you should take care of, like AMSI patching, ETW patching, sandbox evasion, entropy, all these different topics, because hooks are just one part of an antivirus or EDR. So syscalls are not like the one thing that you need to do to be undetected. It's just basically one technique in your toolkit. And also, this kind of goes to the same point, but they are not a silver bullet against EDR or antivirus. They do protect you from hooks, like you're basically bypassing any hook in user land. But still, if the antivirus uses kernel callbacks or ETW threat intelligence, which are both kernel land or kernel level mechanisms, kind of, you cannot really do much about that. So there's a lot of stuff that the EDR can do in which way it will still detect what your syscalls are doing or what you're trying to do. So treat this as just one part of malware development, of just one technique. There's a question: how does ETWTI work? I am no expert on this. I cannot tell you much about it. It's on my list of researching, but I haven't spent that much time, to be honest, on it. So unfortunately, can't tell you that much about ETWTI. Why is the Syscall structure identical for every call? On Linux, you have to populate the stack properly before calling interrupt. I think apparently not. I'm not familiar with Linux syscalls that much, to be honest. But for Windows, it's the same structure for every call. It's just the SSN that is different. Yeah, but before I get into more questions, I get distracted pretty quick. Let me just wrap this up because I just want to give a shout out to some people here, other projects that I could not cover. I linked the slides on top of the chat. I posted them on GitHub. So check out these projects. They're awesome. They have some different approaches, which are also interesting for you to read about. And there's more. And also much love to these people. And I can recommend you to read these blog posts. They were kind of a very good base. I took some of the images from there for this talk. So if you're interested, read through these blog posts. They are great people. They can explain all the stuff very good, and you will probably understand it even better then. But yeah, so far for my talk. Thank you so much for being here and for all the questions and all the interest. I was actually overwhelmed. I didn't expect that many people to come, but I hope you learned a lot and yeah, you enjoyed it. Yeah, thanks so much.
Ever since, that was awesome. Thank you so much for joining us.
Yeah, it was a pleasure. I had a lot of fun.
Let me just try and fix my video here for a second. Okay. And I'll open up the questions. So you actually read a bunch of questions out as you were going, which was awesome.
Yes, but I think I missed some, especially in the beginning.
Yeah, let me go back in the back scroll and
yeah.
Hopefully
do you want to
this
read
is-
out the questions or?
yeah.
Okay.
Let's see what we've got. Okay, I think you actually answered most of these. So one of the questions is, will there be a presentation regarding deinvoke in the near future? Maybe.
That would be awesome.
And what else do we have? Yeah, you read that. Okay, there was a question about the silent patch for Halo's Gate. I think you answered that one as well, didn't you?
Yes, I tried to answer this as well, but as I said, I cannot tell much about that. I wish I knew where I read it. I read it just like 2 days ago. Yeah, that's in some version of Windows, like Windows 11 or something, or some version of Windows 10. They basically changed this by changing a few syscalls to be not in sequence.
So I'll just ask everyone, if you had a question and it wasn't answered, just copy paste it in the chat and we'll read it out. So there's one more question for you here. If we still have some time, can you explain syscall sorting?
Yes, I can, at least in some way. I mean, so I hope I don't get anything wrong. So let me explain this in a very superficial way. So I don't want to get too technical because I might tell you something that's wrong then. But basically, if you look at the screenshot on the right about syscall sorting, you will see that like on top, it's number 27, ZW set information file. The next one would be number 28, and the next function would be number 29. And basically, this means that if you look at all the functions in TDLL, in this case, and just go through them and sort them by address, not by name or anything, just sort them by address. Then you will have the syscall with the ID of 1 at the top if nothing is patched, and afterwards the syscall with the number 2 and the number 3. So all you have to do is sort all the syscalls by address of NTDLL, and then just count from 1 upwards until the last one, and you got all the syscall numbers. Like, this is the basic idea between syscall sorting. And you can check out SysWhisper's free, if I'm not mistaken, how they implement it, and FreshyCodes, as far as I know, is also implementing it. So yeah, maybe have a look at this code or at the corresponding blog post. I'm sure they will explain it some more in depth than I do.
There was one more question. What about using the EDR trampoline to jump back to NTDLL? Are there any drawbacks in doing so?
Are there any drawbacks? Well, if I'm not mistaken, it's not like a drawback, but if you look at the actual call stack that is occurring, you will see that you can still detect that it's a weird syscall because, for example, NT open process was called by our trampoline, but there was no call to open process before. So this kind of would give away that you are using some sort of syscall technique that is not very usual. So this would be the only drawback that I can think of. Yeah, that would be the only thing I could think of.
Any other questions? Did I miss anyone? Speak up, now's your chance.
I think in the beginning somebody asked about if I used AI for malware development or something.
Oh no.
Let me check that in a second.
Is this
Have you attempted,
ChatGPT
or
gonna steal your job? Tell us the truth.
Yeah, the question was, have you attempted to, or are you beginning to see malware written by AI yet? I'm not an analyst, so I haven't seen like malware written by AI yet. And I'm also not a fan of AI, to be quite honest. I like to do my programming myself because I enjoy it. I know a lot of people are using Copilot for writing malware, like super rapid malware development, basically. But I like to do it by hand. So no, I have not experimented with that yet.
It's actually a really kind of relevant question for a lot of the people in this crowd, I think. Do any of these techniques work against common XDRs or EDRs? So for example, Sentinel-1 or Cortex?
I cannot tell you about Sentinel-1 or Cortex in specific because I haven't encountered these in a while. But these techniques by themselves, probably not. But for internal pen tests, I sometimes use my own packer, which is based on Kars van Kooten's packer, actually, an Impact version 1. So shout out to Kars van Kooten. I took his code and basically just changed some things. And I'm using my trampoline Hellsgate variant in this packer. And it's working pretty well against some of these EDRs or advanced solutions. So, I mean, I don't know what telemetry they are. Like, they might be just raising an alert, but not blocking the binary. But if you use these techniques combined with some other evasion techniques like sandbox evasion and so on, I think you can definitely get very far.
So yeah, speaking personally, I think the answer is yes in a lot of cases, and depending on the implementation, almost always yes.
Yes, exactly.
Any more questions here? What payloads are you using? That's about your packer. People asking how to get EDRs. I think maybe that's outside the scope of this talk, but any thought on that or no?
I'm not an expert on all these EDR specific things. I mostly in the internal pen test I encounter the same EDRs like Sophos and stuff. Like I rarely see all these super advanced things in at least the projects I'm doing, so I cannot really give you that much insight, unfortunately. But yeah, in my experience, it works pretty well.
So we're at time. I don't want to keep you longer than we agreed.
Oh, it's fine.
So,
I have some time to stay around. Don't worry.
okay, so we can take a few more questions if anyone has them. Okay, so someone's asking, direct syscall is bypass for malware. Is there anything that uses it in a legitimate way?
I was asking myself the same question actually. Um, I'm pretty sure there are some applications that use these techniques. I haven't done research, like checking, for example, binaries for syscall assembly instructions, but I've seen the weirdest stuff in Windows applications. Like, you know how developing goes, right? People use the weirdest hacks because they need to get some deadline or some feature which isn't intended. So I can really imagine that direct syscalls are used also in legitimate programs, but I don't have any specific example for that.
Yeah, without knowing like a benchmark off the top of my head, I would guess that maybe for performance reasons, some people might do that in like netcode or something, but that's a
Yeah,
guess. I don't
true.
actually have data to back that up. So.
No, me neither.
Yeah, also too for the people asking about EDR, like
Hmm.
Elastic has a free EDR that you can download and use, and it's actually really good. So you can just like go and give that a shot if you want to play around with detections. And I think you can actually put it into like passive mode where it will tell you if you've been detected, but it won't actually like block or upload your files. So that might be a good option for those
Yeah,
people.
and a lot of EDRs also have like trial versions, so you can try to get a trial for some of them. Of course, like some of these companies really don't want reverse engineers and malware developers to get trial versions, so they are kind of
Of course.
picky when giving out these licenses, but you can do that definitely for some EDRs.
Someone asked, what tool do you use to sign your malware, and what do you think is the best EDR XDR base in detection capabilities?
Again, about the EDR XDR, this is I cannot really give you an opinion with a good foundation, so
Mm-hmm.
I don't wanna say anything about that. I really cannot tell which EDRs are the best or are better than others. So sorry, I cannot really give an answer to that. What tool do you use to sign your malware? So in the packer that I use, which is hacked super weird, like it's just a jumble of different projects. I'm using some kind of Java tool actually, I believe, to sign my malware. What is it called again? Let me look that up. Dum, dum, dum. Now, where is it? JSign. I'm using JSign to sign my malware because it's running on Linux
Mm-hmm.
and my packer is Linux based, but yeah, you can use whatever you want. Just a signing tool in the end.
Okay, I'm going to call it. Thank you so much for going over time. Folks, if you have additional questions, feel free to just drop them in the general chat in our Discord. Ever since it's up to you if you want to answer those or not. You're under no obligation to do so, of course.
Yeah,
Um,
sure.
this has been really an excellent talk. I actually learned a lot.
Yeah,
Super
thank you.
clear.
Glad to hear that.
Thank you so much for joining us today.
Yeah, it was a lot of fun. Thank you so much for the opportunity. And again, as I said, if you have any questions or want to chat, hit me up on Twitter. I would love to talk to some of you people. Sorry if I can't answer some of the questions, but I gotta be humble there. I'm not an expert on all the topics. Yeah, thank you everyone. And thank you, Octavia, again.
Welcome.